Welcome. This is a talk that I have been giving recently on the foundations of heuristic search. My name is Nathan Sturdivant. I'm a professor at the University of Alberta and also a CFAR chair in the Alberta Machine Intelligence Institute, which is also known as AMI, which is currently one of the three pan-Canadian AI centers for AI research. And this work is on heuristic search, and we're looking at problems at the foundation of heuristic search. And in particular, we're going to look at problems that have appeared historically on the question of re-expansion. And this is an overview talk that I've been giving recently at a number of different institutions, and I thought it'd be great to record a copy here to put on my YouTube channel and make it available to other people. As this is an overview talk, we're going to cover a large range of material rather quickly. But in doing so, we're really going to touch on things that, for instance, elsewhere on my channel, you can find more details on. But the point here is I want to draw this connection of search and re-expansions in search and show how it permeates many, many, many heuristic search algorithms, how it impacts the best case, the worst case, things like this. And so we're going to just have this sort of whirlwind tour of heuristic search and how re-expansions have shown up there. And one of the things about the field of heuristic search is that actually the field is quite old. It's over 50 years old, but there's actually a lot of work that isn't widely known. Oftentimes people only know what is covered in the first couple of chapters of Russell and Norvig or something like that. And so people may not be aware that actually there is new research going on in this field. And so this will also give a little bit of an overview of that. But my goal here isn't actually to explain the research, although we will do some explaining. The goal here is to give this high-level overview of where this notion of re-expansions occurs again and again during search. To say a little bit here about my lab as a research professor, or as a professor, I do work in traditional games. So we look at things like machine learning in games, solving games. We're looking at heuristic search algorithms, so just basic fundamental search. We've looked at multi-agent pathfinding, a lot of work there. I've done historical work on pathfinding in games. That is understood much better than it was 20 years ago. We're looking currently at notions of the entropy of a puzzle, how to do AI-assisted design within games, particularly within puzzles. And I do have MSc and PhD positions open in my lab. Let's go to heuristic search and shortest path problems. So what are the types of problems that we're trying to solve here? I'm going to try and avoid formality where it's not necessary. So in a lecture, in a course, I might give very much more formal definitions. We're going to only do it when absolutely necessary here. So heuristic search is a problem of finding a path in a world or in an environment. And if we were to think about a game environment, so these are clips from Nightingale, which is a game by Inflection Games that came into early access in February 2024. I'm working with Inflection, and I worked with them on some of the details around pathfinding. And so some of the large creatures in the world, as they pathfind across the world, we need to know how do we get them a path that physically goes through the world. So you'd see this with GPS, you'd see it with robots, other things like this. But pathfinding can also be looking at abstract problems like the Rubik's Cube. So if we think about the Rubik's Cube, the path it's a sequence of actions that are applied to transform a start state into a roll state, or Towers of Hanoi is the same sort of thing, but it's a series of actions. So all of these are paths, a series of actions that transform the start state into a roll state. There's other class of algorithms that we're not talking about here that have other complexities to them. Okay, so I'm not going to let these animations of the one on the right finish, but we just saw our optimal solution of the Rubik's Cube there. And let's talk about, what is the history of search algorithms? So one version here, a very simple version that people are often aware of is there's Dijkstra's algorithm or Dijkstra's search, which it came in 1959. That introduced this notion of doing search and what we'd call a best first search. And that was refined in 1968 with A*, with the introduction of heuristics. And then in 1970, Pohl came up with the notion of weighted A*. He didn't call it that at the time, but it's what's known as weighted A*. And for many people, this might be, hey, this is what I know. Dijkstra's becomes A star becomes weighted A star. If we know a little bit more, we might come in here and say, well, if we're in memory-bounded state spaces, then if we want to solve something like the Rubik's Cube, you need an algorithm like IDA star, which was invented in 1985. We also have a notion, and depending on the background, your background, some people do learn about bidirectional search. So that was first invented in 1966. That's a brute force bidirectional search, not a bidirectional heuristic search. And for many people, hey, this is the timeline of search. And we notice that a lot of this goes back 50 years, 1970, 1968, 1966, with the exception of IDA star coming in 85. And what we're going to do is we're going to look at all of these different approaches here and how re-expansions play into these algorithms and understand how they play into the worst case and other things like that. Okay, so just to give you an example of this, starting with a practical example, on the left-hand side and on the right-hand side, we're going to solve exactly the same problem. On the left-hand side, we have a consistent heuristic, and the right-hand side, we have an inconsistent heuristic. What that means exactly, we're not going to go through the math, or I'll show it briefly later. An inconsistent heuristic doesn't obey the triangle inequality, so that's one way to think of it. But in both of these cases, so let's watch this run. So on the right-hand side, by building an inconsistent heuristic, what the consequence of that is I have to do state re-expansions. And those are the states in purple on the right-hand side that have been, what happened is the search visited them and then revisited them. And on the left-hand side, I have a consistent heuristic, but the consistent heuristic, you can see, is actually not as strong as the inconsistent heuristic on the right. So even though on the right-hand side, we had to do state re-expansions, those purple states, we can see that overall we did less work, even if the purple ones count twice, than the work that was done on the other side with a consistent heuristic. So there's some interest in thinking about these things and what their impact is. Now, slightly more formally, what we're going to say here is imagine that I have a search. It comes to some state here. And after I reach that state, I'm going to do some amount of work here, which we've animated off to the right. And then the question is, I find another path back to the same state, a shorter path to that state. And the question is, should I redo that big piece of work on the right-hand side, or should I just let it go and not have to redo it? And that's what we're looking at in this talk. Now, many algorithms are going to face the question of state re-expansion. So all of the ones here face the question of re-expansions. And actually all of them, or almost all of them, we've had significantly improved our understanding of what happens in these cases in recent years. And one thing in particular is the cause for state re-expansions and everything except IDA star is related in some way to the notion of inconsistent heuristics. You don't have heuristics in Dijkstra's algorithm, so it's not quite the same, but we'll explain that in a minute. Now, some people might say, Nathan, why are you here talking about, these algorithms that are old algorithms that they're really not, where the state of the art is or where things are interesting these days. The future is in, generator, like language models or in image generators and things like this. And so here what I did is I made two queries to Meta's image generator. The first one I said, tell me what a heuristic search algorithm looks like. And this is the picture that it gave me. Sorry, my picture's covering it up. A person writing a heuristic search algorithm to solve a maze. So we can see that's how that was imagined, solving a maze there. Now, we could say, hey, isn't that where all the interesting things are? We really should be working on these sorts of algorithms. And the answer to this is yes, there's a lot of interesting work going on in these areas of AI. And there's a lot of actually open questions. Even in my lab, we're looking at questions of how do you combine together the types of things that we can do with machine learning with the type of traditional things we do in areas like search. And if we think about that question, then what happens here is that we have to think about what type of data do we get from machine learning algorithms? Is that data going to look like the data we get from maybe some of our traditional algorithms? And the answer is the type of data we're going to get here is going to have properties like inconsistency. And therefore, if we want to understand and properly integrate things like machine learning into search, then we need to think about inconsistency and its relationship to what's going on there. So I'm not going to talk about that any further in this talk, but it is something that we do need to be aware of and be careful about. Okay, so we're going to go through and we're going to introduce a bunch of algorithms. We'll talk about the problem it's solving and then talk about some recent solutions, and we'll look at it through the lens of re-expansions. So the first one we're going to look at is Dijkstra's algorithm, and this is a 1959 paper, a note on two problems in connection with graphs. First, we can take a look and we can watch how Dijkstra's algorithm works. It's solving a problem here. We saw the little arrow at the beginning from the start to the goal, and we can see on this particular problem, it's going to expand almost in every state in the entire state space. Similarly, we could go into a road network. So this is the road network of New York City. This is Manhattan here. And if we run a similar search here and do a Dijkstra's algorithm search, we do, for solving this particular problem, we do a massive amount of work expanding almost every state in the graph to try to find one particular path through the world. So Dijkstra can be quite expensive. And how does this work? So we're going to establish some things that we need here that'll connect many of these algorithms together. We're going to let g of n be the cost of the best known path from the start to some node n. And then we're going to expand states from low to high g of n. Okay, and that's Dijkstra's algorithm. And we're going to assume initially that all costs are going to be cost between any edge between two nodes or two states is going to be greater than 0. And so the problem looks like this. I have the start state, I have a goal state, I have a path to some state u where all the states between the start and u have been expanded. U has not yet been expanded. Expanded just means that we've taken it off a priority queue, we've generated its successors, and then we put it onto a closed list. So here u is sitting here waiting to be expanded, and we're going to choose the state with the minimum g of u to expand next. Okay, and so that's Dijkstra's algorithm. It's well known. It's not too hard to implement, and it's been around for quite a long time. Now, what about the question of negative edge costs? So very often, people will say, Dijkstra's algorithm. Well, Dijkstra's algorithm is great when you have positive edge costs, but Dijkstra's algorithm doesn't work when you have negative edge costs. And that's actually not true. If we look, there's a paper by Johnson in 1973 that looks through and says, it depends on how you implement Dijkstra's algorithm. As long as you're willing to re-expand states when you find a shortest path, a second path that goes to a state, then we should be willing, then if we're willing to do that, then Dijkstra's algorithm will be able to handle negative edge costs. However, the worst case complexity of Dijkstra's algorithm is that you could have an exponential re-expansion of a set of states. So you could have n states in the middle of a graph, which are expanded 2 to the n times. And this is an example of where this can occur. And what we're going to do here, so I'm not, there's too many nodes here. This demo is available on my webpage, but there's too many nodes here to draw all the edge costs. But we can see the edge costs here actually growing exponentially. And if we watch how Dijkstra's algorithm runs here, every other expansion is on this node here at the bottom. And then every fourth expansion is here, every 8th, 16th, 32nd, 64, 128, 256, 512. And so eventually what happens is that we get all the way to the end until we finally expand the shortest path here. Shortest path goes all the way around, but it takes Dijkstra's algorithm an exponential amount of time to find it. So Dijkstra's algorithm has this exponential worst case complexity, and that's not great. Now the Bellman-Ford algorithm fixes this, and I'm going to take some liberties to describe the Bellman-Ford algorithm. But one way we could think of the Bellman-Ford is to say, instead of going greedily from low to high g cost, what we're going to do is just iterate through all the states in the state space and expand them. Iterate through all the state space and expand them. And we just do this over and over and over again. And if we do that, the cost is, I'm going to do that iteratively. I'm going to expand every state, which on the types of problems we're looking at is going to be something like v squared, or the subset of v nodes that this happens on. Well, if we have a subset of n nodes or v nodes, we're going to sort of switch back and forth between the two, whether using graph or a sort of A-star terminology. But here we can have a v nodes as long as the branching factor or the degree of a node is constant, then we'd expect to see like v squared time to run Bellman-Ford. Okay, So this is going to give us this table. We're going to build this up here. And yeah, so n could be a subset of nodes in V. I said at the bottom here, so Dijkstra's algorithm is going to do re-expansions if we have negative edge costs as a worst case complexity of 2 to the n. Bellman-Ford, there are a bunch of different inventions of the same algorithm. You must do re-expansions, and in the worst case, it'll do n squared re-expansions. Okay, so let's go to our next algorithm, which is bidirectional search. And the first algorithm here that was correct was by Nicholson in 1966. And Nicholson drew this picture in his paper. He said, if I have a search problem on the left-hand side here, a disk that grows out, then what we could say is, one big disk is more work than 2 small disks that are going from the start and the goal simultaneously. And in polynomial domains, this gets you like a factor of 2. But in exponential domains, you'd get a much, much larger savings because of the exponential growth of each of the frontiers. So if we show this, this is a city map of Denver, and we watch a bidirectional search here, we can see we very much do get these 2 circles that are going here because Denver is on a grid, so we get more like squares than we get circles. But we see here that these 2 searches could be smaller than one large search, which might encompass a lot more of the city. So bidirectional search, if we're going to define our general problem here, now instead of just having a g cost, we're going to have a forward g cost, which is the cost in the forward direction, and we're going to have a backwards g cost, which is cost in the backwards direction. And there's a number of different variants you can do here, but for simplicity, we're going to say, let's just choose the lowest g cost from both frontiers to expand that one. So it looks something like this. I've got a picture here. I've got a bunch of states U in the forward direction. I've got a bunch of states V in the backwards direction. They all have corresponding G forward and G backwards costs. And we could then essentially run something like Dijkstra's algorithm. If you were to put them all in the same frontier, you could just continually to choose one with the smallest G cost, and that would give you a bidirectional search. Now, what about negative edge costs? So as far as I'm aware, this problem actually hasn't been analyzed. You're going to have the same sort of problem as Dijkstra's algorithm in that with negative edge costs, you might have to do re-expansions. The problem is actually termination. If you try and terminate and you want to show that you're optimal, well, there could be a negative edge cost somewhere. And if you don't discover that, then you may not be optimal. So that actually complicates this quite a bit, which is perhaps why it hasn't been analyzed, or it makes it less interesting. Okay, so we continue here. We've got bidirectional Dijkstra. This is 1966. And if you have negative edge costs, then you're going to have to do re-expansions. But as I said, this has not been well analyzed. Okay, so let's move forward to 1968 and look at A star. So A star, we can compare Dijkstra's algorithm to A star, and we can see that A star on the right-hand side is goal-directed, where Dijkstra on the left-hand side is not goal-directed. And as a result of the goal-directedness of A star, it's going to do a lot less work than Dijkstra's algorithm to solve the same problem. Okay, so what's our definition? I guess we'll wait for Dijkstra's to finish here, but we see it takes quite a long time to do so. There we go. Okay. So what is A star? So just like before, we're going to have our G cost. That's the cost of the path getting from start to some node n. But now we're going to have H of n, which is an estimate to get from n to the goal. And now, instead of going from low to high G, we're going to do G plus H. So we're going to be thinking about the total path cost from all the way from the start to the goal. And depending on like what you're trying to prove, we often assume either that the cost of an edge has to be positive, but it could be 0. So either positive greater than some epsilon, or we could allow it to be 0. Again, depending on the assumptions or what you want to prove about A star. And usually we assume that H is both admissible and consistent. So admissible just means that for every node, n, the heuristic of the node has to be less than the true cost of n to the goal. So it's not overestimating. Consistent, we're going to write in this way here, says that between 2 nodes V, the difference in the heuristic value has to be less than the cost between those nodes. We're going to use this form of the equation a little bit later in the talk. So we see that H of U minus H of V is a bound on the cost. It's a lower bound on the cost between U and V. So we'll see that again later. So our picture of a unidirectional search algorithm then is we go from start to U. From U to the goal we have as a heuristic estimate, and this is what we're doing in A star. And if we go with A star and we take a problem like this, we saw this search earlier. This is A star with actually a very accurate heuristic here. This is using a differential heuristic. We're able to search around here, and very, very quickly we can get, because of the accuracy of the heuristic, we can get to the goal. Okay, so now the question is, does A star have to do re-expansions? And the answer is yes, it has to do it if the heuristic is inconsistent. It ends up we can show that an inconsistent heuristic is equivalent to negative edge weights in Dijkstra's algorithm. And you can take actually any problem with A star and you can do this conversion to just having your edge costs, not having your heuristics, and then it would be solved with Dijkstra's algorithm exactly in the same way that it would be solved with A star. And so that tells us that that exponential worst case is going to be exactly the same for A star as it will be for as it was for Dijkstra's algorithm. And we see people understanding this. So Martelli in 1977 first saw this and addressed it, and he built algorithm B. Algorithm B has O of V squared complexity in the worst case. And algorithm B actually looks in so many ways like Bellman-Ford because again, a high level omitting some of the details of how it really works. What algorithm B is really is it says expand one new state using, in the worst case, would expand one new state in the A star way, and then to say go back and re-expand every state that you've expanded again in using actually only G costs. And if you do this back and forth, you do one A star and then you do all your states as sort of as a Dijkstra and back and forth, then in the end, you'll get to V squared as your worst case. But that does mean that with A star, we can take that worst case and we can bring it down from 2 to the n to n squared, again, depending on how you're talking about V or n. Okay, so A star, if you have an inconsistent heuristic, the worst case is 2 to the n. This also requires an exponential distribution of edge costs or exponential precision if you're going to make the values really small. So if you actually don't have this exponential range of costs, then you're going to see n squared in practice. And we can bring that down by algorithm B in 1979 to be n squared. Okay, so we got A star and we had bidirectional Dijkstra. So Dijkstra, bidirectional Dijkstra, A star. The natural question the year after A star was introduced is, can we do bidirectional heuristic search? This is Ira Pohl. He's the same guy who invented weighted A star. Also was the first person to look at bidirectional heuristic search. And it's a very natural question, right? If we do Dijkstra to bidirectional Dijkstra, we just expand the minimum G cost. We could go A star. Pohl called this BHPA, and we could just expand the minimum F cost. It seems like this should work really well, but it ends up it didn't work well in practice. And there were a couple explanations that were given historically. If you look at all these different pieces, there's actually quite a bit here. I'm going to highlight one piece, is that we think about the forward and backwards search. Pohl's explanation was the forward tree and the backwards tree were almost entirely separate, almost had entirely complete solution paths in the different directions. And so the two search frontiers basically were missing each other. And so the bidirectional work was wasted because they didn't meet until much later in the search than we would hope. This is drawn pictorially in Nilsson's 1980 textbook, and he showed this picture here that the frontiers are missing each other. So this is one of the traditional explanations of what was going on. But we see, this was revisited a number of different times during the literature, and Kindle and Kynes came in 1993 and said, for more than 2 decades, the consensus that the search frontiers are missing each other. However, and then they summarize this later in a later paper, 2 problems. One is the frontiers go through each other. And we think about if the 2 frontiers go through each other, what's actually happening here is that we're re-expanding states. That means the states where, as we expand forward and as we expand backwards, we expand the same states in both directions. So this is the problem of doing state re-expansions. And the second problem was, hey, the frontiers meet, but it's really hard to prove the solution. And so we spend a long time trying to prove the solution. So I'm going to go over some of the recent results on bidirectional search and as they relate to these 2 problems of the frontiers going through each other and the problem of proving. Okay, so some of the work that was done building on the initial algorithms that didn't work very well started to look at the assumptions. What could we do if we assume consistency. And so Qua in 1989 proposed an algorithm BS star that could avoid the frontiers crossing given the assumption of consistency. And Kindle and Kynes in 1997 showed that if you also assumed consistency, that you could make other improvements to the heuristic to the heuristics used during the search, and you could actually improve performance. The problem here, though, is that there's actually no theory of bidirectional search at this point. Why are the algorithms terminating late? Well, what is the work that has to be done? What does it mean for an algorithm to be optimal? What is the best case? Is it that we just don't have good enough algorithms? Or is there some theory that tells us we can't do any better? And so we want to look at that. And in order to understand that, let's look at the unidirectional problem first. So in the unidirectional problem, we're searching, remember, from the start to U, and we have a G cost, and then from U to the goal, and we have an H cost there. And so this is the F cost, which estimates the total solution cost. And if we have a admissible and consistent heuristic, then what our theory says, so this is the F cost here, is that any state that has an F cost less than C star, where C star is the optimal solution cost, we must expand U. Okay, so the theory here tells us there's certain states that must be expanded, and then it was shown that A star expanded exactly those states, and therefore A star was an optimal algorithm because it actually expanded up to tie breaking. At the last layer, it expanded every state that needed to be expanded. It didn't expand any of the states that didn't need to be expanded, and then the ones that we didn't know, there's just tie breaking there that determines it. So that's great. To have that theory. And if we look at the bidirectional problem, then there's a number of different ways we can formulate the bidirectional problem. For right now, we're going to assume we only have a heuristic to the goal state on the right-hand side, or a heuristic to the start state here on the left-hand side. And when we do this, then, right, we can draw our same picture here. And the question is, what bounds do we possibly have that we could use to try and write down a theory? And so the first thing we have is, well, we could have a zero cost edge in between here. So we could have a path between that goes from start to U to V, and V to the goal. That's just simply the sum of the G cost plus a zero cost edge in between. But we also know, for instance, that going from start to U and U to the goal is going to be a bound on the total path cost of start to U to V, and V to the goal. So we could use that. And we also know in the backwards direction, we could go from the goal to V and then V backwards to the start. So this backwards heuristic to V could be used as getting a bound. And so this theory was developed in 2017. And sorry, I didn't say it earlier, I meant to say it, is that the theory of A star, there was some theory in the original paper. There's a very, very comprehensive theory that was published in 1985. And that's where we really see all the cases handled in the lowest level of detail. Here in 2017 is the first time that this theory was published of bidirectional theory. And what it said is we're going to define the lower bound of a pair of states, U and V, to be the maximum of the forward F cost, the backwards F cost, and the sum of the G costs in each direction. And now the theory of bidirectional search says if the lower bound of a pair of states is less than C star, then we have to expand either U or V, but we don't have to expand both of them. And this is very different than the unidirectional theory, because the unidirectional theory said every state that meets this condition has to be expanded. But what we're saying here is actually only the states that of the states that meet this condition, you either have to expand in the forward or the backwards, but not both. And the way we can understand this is we can look at a sample problem here. So here's a sample graph or a sample problem on a grid. And in the red problem, we're going to think about, here's the states that in the forward direction have F cost less than C star. So those are necessary in the forward direction. Here are the states in the backwards direction that have F less than C star. And this gets us 2 of our 3 conditions, but it doesn't give us all of our conditions. So we need a third condition here. And to think about this third condition, we have to think about pairs of states that come from the red states and the blue states. And the way we're going to handle this is we're going to pull these states out here. We're going to label them each with their G cost. And we have this third condition that says I need to expand a state if the sum, so we can think about a state here and a state here, I need to expand a state if the sum of the g costs, which are written inside these circles, is less than c star. I need to do either the left or the right. So we can actually say, in this problem, c star is 10.5. So then we could actually just write down here, between any two states, if their sum is less than c star, then I can draw an edge between them. And this gives us a bipartite graph, and it ends up that if we find the vertex cover, the minimum vertex cover on this bipartite graph, then we actually, it's going to tell us the minimum number of states that have to be expanded according to these conditions. So we're going to call this the must expand graph. We'll do just a couple things here to show what happens in this particular case of front-to-end heuristics. Okay, so we can take these states here. There's a lot of states here with duplicates. So what we're going to do is sort them, and we're going to take the duplicates, and we're going to write the number of duplicates of each node next to the side, next to the node on the side. And then what we're going to observe here is that a particular state is going to be connected. If we watch here, it's going to be connected. It's always connected to the bottom node and then up until it reaches some node, and there's some maximum node that it connects to, and it never connects higher. Because these are sorted, then basically, once this reaches 10.5, we don't connect, and if it's 10.5 here, it'll be 10.5 for every node above it. So what that means is instead of drawing all these edges, we can just draw the last edge. And then on this problem, if we think about 10.5, what we're going to choose is, it ends up that solving this problem ends up that we're going to choose a meeting point here, and we're going to choose basically how we're going to meet, because we have to expand either the left or the right hand side and everything above it for anywhere that there's an edge between these nodes. Okay, so I get to choose where I'm going to work, and the amount of work that I do is the sum of the numbers on the left plus the sum of the numbers on the right. And all of these are vertex covers of this particular problem. And on this particular problem, it ends up that going in the forward direction, that is on the red side, all the way will do the minimum total work. But at least on a front-to-end search, my heuristics only get me to the goal. This is exactly what the problem looks like, and here's how we could find the minimum work. Now, in practice, of course, you have to solve the whole problem in both the forward and the backwards direction to compute what the minimum is. And we can't afford to do that in practice. So A star as an algorithm says repeatedly expand the state with the lowest f of n, and that's optimal. We have a new algorithm called near optimal bidirectional search, and it's near optimal. It finds optimal solutions, but it's near optimal in the number of expansions. And this just says repeatedly expand both states in the pair of states with the lowest lower bound. It ends up that we can, in using regular data structures or relatively simple data structures, we can actually find the pair of states with lowest bound efficiently in this particular case. And it ends up, though, that NBS may expand the same state in both directions. However, NBS is guaranteed to do no more than 2 times the minimum number of expansions of any algorithm. And it ends up that every bidirectional algorithm will do at least 2 times as many node expansions on some problem in the worst case. There's no way that you can there's no way that you can do the minimum on all problems. So this is really interesting, because what it says is in this condition here, this is the condition, the NBS condition where I have these front-to-end heuristics. We don't have any knowledge of whether a heuristic is consistent or not, but we're actually analyzing the behavior of a consistent heuristic, which is a little bit funny theoretically, but I can't go into that further here. It just says that NBS is going to be within a factor of 2 of optimal. And the NBS framework can actually be applied anywhere where any bidirectional search where we can write this lower bound, but may not be feasible to compute the pair of states with minimum lowest bound at any step of the algorithm. But if you can do that, then you'll always have a 2 times bound for your bidirectional search. Okay, so continuing on here then, this is the paper that describes that algorithm. Continuing on then, the interesting thing here, though, is that we are doing re-expansions, and it doesn't hurt us in terms of the minimum number of node expansions or the behavior overall. So at least in this case, re-expansions can be bad, but since we're no more than 2 times overall, there isn't actually a large overhead in this type of re-expansions that we see. Now, this doesn't talk about what happens if we have a consistent heuristic. And so the theory was actually extended to consistent heuristics in 2018. And the picture here looks a little bit different because what we're going to do, we still have the same g in the forward and g in the backwards, but now we have the distance in between here. And what I can do if I have a consistent heuristic is, if you remember, the difference in the heuristic values is less than or equal to the edge cost. And so the difference in the heuristic values here gives me an estimate of the cost of the edge between u and v. And so this is more accurate. But when I have this sort of heuristic calculation, it ends up finding the pair of states with the minimum heuristic is no longer efficient. So the new theory here is we're going to define, so we have F forward, F backwards, but now we have this center heuristic, which is just what is my heuristic that I get from consistency between u and v, which we won't write out fully. But anyway, with this picture, one thing we can notice here, though, is that in the forward direction, we are just doing a star, that's g plus h. And in the backwards direction, what I'm getting is g forward minus h forward. And this is an idea that was actually invented by Kindle and Kynes. And they proposed this use of inconsistency. And when we start to look at the theory of bidirectional search, then we can actually see that this comes, that what Kindle and Kynes did fell out of the theory, but they didn't have the theory at the time to back up what they were doing or to explain or to justify what they were doing. And what's really interesting here, there's a lot of work that's been done in the case recently about how to do bidirectional search with consistent heuristics, is that it ends up that because we can't do this computation efficiently of the pair of states with the minimum lower bound, what we end up doing is we end up approximating it across an entire frontier, and then we can do that approximation efficiently. So this can be approximated across all states, and then we get a star plus this approximation. I'm not going to go into that any further here, but I do want to point out we have some recent results. These haven't been published yet, but that show for the first time actually, because historically bidirectional search didn't work very well. But here we've shown on some of the hardest problems with state-of-the-art heuristics, in this case state-of-the-art consistent heuristics, that we can solve some of these really, really hard problems doing far less work in terms of time and in terms of node expansions than we would do in a regular IDA star search, which would be a typical approach to a problem like this. So this is interesting because with the addition of consistency, with the assumption of consistency, we see bidirectional search is now starting to show, particularly on really large problems with state-of-the-art heuristics, that is the well-performing algorithm. Okay. So that was a little dive into bidirectional search. And what we see is BHPA star, or BHPA, as an algorithm that has re-expansions. When the frontiers meet, there's just a chance that the frontiers go through each other and we do re-expansions. There's no worst case analysis that's been done there. Practically speaking, it's a factor of 2. BS star uses a consistent heuristic to avoid doing re-expansion, so it doesn't do any at all. That's the algorithm by Qua. NBS in 2017 has no knowledge of consistency, and it's guaranteed that it does no more than 2 times the minimum number of nodes, and then some fraction of that could be node re-expansions. But we have an upper bound on that, which is a nice upper bound related to the optimal number of nodes or the minimum number of nodes that are needed to solve a problem. And then BAE star with 2012 also is able to avoid doing re-expansions because of its use of a consistent heuristic. So that seems to be really valuable. Okay, so let's turn back then to A star and IDA star. So these, again, are our fundamental algorithms. 1985, Corfin introduced IDA star. And we said that, Dijkstra's doing re-expansions when there's negative edge costs, and A star does it if the heuristic is inconsistent. And it ends up that both Dijkstra and A star have 2 to the n expansions in the worst case, but practically speaking, if we don't have exponential edge costs, then we're going to see n squared. And so what I'm going to show you first here is what happens to A star in this particular problem and what the structure of this problem is. So this is an A star n squared example. And then we'll look at BGS, which is a new algorithm. So A star, what it's going to do here is we have this top structure of this problem and then the bottom structure. And what's going to happen basically is we're going to come down here and we're going to find a path to this node, and then we're going to do some work on the bottom. And then we're going to go to the next node and we come back. And then the question is, do I redo this work? Well, it's going to redo the work. And every time it comes to a new node on the top, it's going to do up until the limit of the number of nodes here. Basically, it's going to do all the nodes here. In practice, it grows by 2. But we do a little bit of work on the top, and then we're going to redo a bunch of work on the bottom. So we'll watch A star here. We see that it's going to do each new node here, and then it's going to redo everything on the bottom. So the purple states are ones that have been redone. And as we continue through the search, now at this point, we'll do one up here, and then we'll redo everything on the bottom. So if you have n nodes on the top, and then we have n nodes on the bottom, for every new node we see on the top, we're going to do n nodes on the bottom. That's going to give us n squared re-expansions in the subset of states. And if we want to get rid of this worst case behavior of A star, or algorithm B, or some of the other ones that came after it, there's B prime and C and some other things like that. There's a new algorithm called budgeted graph search. What budgeted graph search is going to do is it's not going to go through these nodes in order, but it's going to basically jump ahead. So we can watch this here. And by jumping ahead here, so we're doing 3, but we see now we're going to jump ahead and we do 6 on the top, and we'll jump ahead some further. By jumping ahead, what's going to happen is it avoids getting this n squared behavior. So this jumping ahead allows it to, in this case, it's actually entirely restarting the search, but it's going to jump ahead, and then it doesn't have to do as many re-expansions, and it's going to solve the problem more efficiently. So it ends up that A star's worst case can actually be ameliorated of re-expansions, and let's see how this is done. And it ends up that actually the same approach that does this also fixes the worst case of IDA star. So the approach here is an algorithm called, it's a general framework called IBEX. And if we apply this to, in a certain way to graph problems, something like A star, then the complexity of the algorithm is n times the log of C star, where C star is the optimal solution cost. So of course, if our solution cost grows exponentially, then this could still be n squared, but on many, many problems, then this is going to be much smaller than O of n squared. And this is described in a 2019 paper. And if we try to analyze what is going on, what is causing re-expansions in practice, there's actually 2 causes that are going on. So if we think about, if I have an A star search that's doing a bunch of re-expansions, you could just ignore the heuristic. You could use Dijkstra's algorithm. Because the underlying costs are actually not negative, it's only the heuristics plus the costs that give us negative values there. Then what that means is that if we just ignore the heuristic, we could actually use Dijkstra's algorithm. But the heuristic could actually be really effective in pruning states. You know, there could be billions and billions of states that are being pruned. So ignoring the heuristic is actually a bad idea. So there's this tension of like the heuristic could be misleading, but the heuristic actually could be very, very powerful in helping me prune the search. And so if we want to solve this problem, what we can think about is imagine that I just knew what the solution cost was. So if I knew the solution cost, what I could do is I could guide the search. I could just run basically a Dijkstra search. And anytime I found a state with F cost that was greater than the solution cost, I would prune it. Okay, so this algorithm is called breadth-first heuristic search. It was introduced in 2004. And if I knew the solution cost, I would run this once. It would expand the minimum number of nodes, would only expand basically the necessary nodes plus maybe some tie breaking. And it would actually be a very effective algorithm. So if I just had an oracle that could tell me what C star was, then I'd be in really good shape. So what we're going to do is we're going to figure out how to build an oracle that has a small overhead. Okay, and what we're going to do is, and we have to do 2 things simultaneously to do this. We're going to estimate what C star is, and we're going to do this using an exponential search, which I'll show in a second. And then when we do this, we need to control the cost of what if I search with an estimate of C star that's too large, that might be really, really expensive. So I need to control that. We'll use a budget to control it. And the question I want to know is, what is an F cost that I can fully explore using K expansion? So K is my budget in this case. So you can think here, this is every F cost that I could use to solve the problem. Okay, and I'm going to ask, I have a budget of, let's say, 1,000 nodes. Okay, I want to know then, what is the maximum F cost that I could do for 1,000 nodes? If I can answer that question, then I could say, well, give me the F cost for 1,000 nodes, then give me the F cost for 2,000, 4,000, 8,000, 16,000. And in the end, the solution is going to be, some F cost there. And the overhead, the maximum overhead that I could get is a factor of 2, which is a constant overhead. So we're okay to pay a constant overhead there. So we're going to think about what is the maximum F cost. So what we're going to do is we're going to do a binary search here. So let's suppose this is the maximum F cost for this particular problem that I can solve using 1,000 node expansions. What we're going to do is we're going to query. So we're going to do a search. We need to know, am I above K, let's say 1,000 expansions, or am I below 1,000 expansions? So we're going to start here, and this is an exponential search. So we're going to grow this value exponentially, where each of these array entries are my estimate of the F cost. So I say F cost 1. It says, no, that's less than 1,000. F cost 2, F cost 4, 8, 16, 32. All of these are less than 1,000 node expansions. And when I get up here, 64, then I'm greater than 1,000 expansions. And the key here that's really important is there's a greater than there that you can't see behind my picture. So I apologize there. But the key here is, what is the cost of this query? So the cost to knowing that I've done more than 1,000 node expansions is not the cost of the search, but it's just 1,000 node expansions. Once I've done 1,000 node expansions and not solved the problem, I know that I'm not going to find a solution to the problem. So I do 1, 2, 4, 8. At this point, I know it's between 32 and 64. And so now I'm just going to do a binary search between in here. Each of these searches at most costs K expansions. And so with a binary search, what I see is it's a log number of steps to get a lower bound and an upper bound. It's another log number of steps to go between the lower bound and the upper bound. And so within a log amount of time, I can actually find the F cost that will give me exactly K expansions. And in the end, when I want to find the solution, so what F cost, so if I know for C star, what is the optimal solution, the cost of it is going to be the number of nodes I need to expand to do the optimal solution. And then I'm going to have to expand that a log number of times. So I'm going to do that again and again. A log number of times I'll do that number of node expansions to be able to run this estimating procedure. Okay, so I have some other videos on this and some papers and other things if you want to go into it in more detail. But let's just look at how this runs in practice. So we're going to run on the left-hand side and the right-hand side simultaneously. On the right-hand side, we're running budgeted tree search. So this is IDA star and budgeted tree search. This is exactly the same procedure as it would actually run in A star. Here we're just doing a tree search instead of doing a breadth first heuristic search. And on the left side, IDA star, the costs are such that IDA star is going to do essentially 1 extra node every expansion. Budgeted tree search is going to be doing this exponential growth. And so we'll watch a budgeted tree search, and then we'll come back and see how much progress IDA star has made. So as we run it, what we see is that budgeted tree search, you see it jumps this tree up and down as it's trying to estimate the solution cost. And because it's growing this exponentially, it very, very quickly finds where the cost C star is going to be and is able to find the solution very, very quickly. On the left-hand side, IDA star is going 1 node at a time. It's doing 1 extra node or maybe 2 extra nodes at a time. And it's actually going to take a really long time to solve this, so we're not going to wait for it to solve the problem. Okay, so if we want to summarize this, re-expansions are actually a really big problem in IDA star search if we have an inconsistent heuristic. Actually, inconsistency doesn't affect IDA star. It's non-uniform edge costs that affect IDA star. In A star, it's an inconsistent heuristic. They both sort of cause the same problem, and they both can be fixed by this IBEX approach. Budgeted graph search is the version for A star. Budgeted tree search is the version for IDA star. And log C star node expansions. And in terms of IDA star, it ends up that budgeted tree search basically runs exactly like IDA star unless we start to see the worst case, and then it gets this other improvement. So there's no reason why we shouldn't just use budgeted tree search all the time. For budgeted graph search, it's a little bit complicated. We addressed this in the 2022 paper. But what's actually really interesting here is that we showed that if A star is only going to each step expand states with F less than C star, it doesn't want to ever expand a state that's not necessary, f greater than c star, then any algorithm that does that, actually not just a star, is going to be guaranteed to expand at least O of n squared states. It's only by actually overestimating, doing states with larger f costs, that we're able to avoid this n squared and get down to n log c star. So it's an interesting algorithmic feature of what's going on there. Okay, so finishing up this table here, or almost finishing, there's one more topic we're going to look at, IDA star. In the worst case, sorry, I'm covering it up here, but A star is going to have n squared expansions in the worst case. If the iterations grow fast enough, that gets amortized away, but in the worst case, it'll be n squared. Budgeted graph search brings us down to n log c star. Budgeted tree search is n log c star, and that's improving both IDA star and A star algorithm B. So the last thing we want to look at is weighted A star. So weighted A star is in this paper from 1970. So Ira Pohl was really busy. 1969, bidirectional search. 1970 was looking at suboptimal search. And in this paper, he proposed that we weight our heuristic. And if we do so, we might do much better. So on this example, the A star is actually going to run faster in terms of nodes per second. So it's going to finish a little bit faster. But if we look at the total area of the nodes that are expanded, then what we see is that the weighted A star on the right-hand side is doing less expansions than A star is on the left-hand side. So that's great. If we don't need optimal solutions, we can relax the requirement for optimality, and our search is easier. So weighted A star is same problem definition here, G of n from the start to the n, H of n from n to the goal. But we're going to expand states by f of n is G of n plus W times H of n. So W is an inflation factor. It's also a bound on suboptimality. But the interesting thing is that by weighting the heuristic, this is equivalent to creating an inconsistent heuristic. So that means that weighted A star is going to have all the same problems that A star had when we think about inconsistency and the worst case. Now, the question is, historically, how has weighted A star been described in terms of doing re-expansions? So the original algorithm in the paper, HPA, says that as we put nodes into the open list, so if we expand a state and it's already there, we're not even going to look at that node. We're just going to throw it away. And now there's some assumptions here that made it maybe reasonable in the rest of the paper, but in general it said don't even look at duplicates, don't even update them, just ignore them and continue the search. If there was a later algorithm that was introduced later in the paper, or an aside that was said, and it said, hey, maybe what you want to do is if you find a smaller value, then remove it from the open list and put the new value in, and then maybe you want to do re-expansions. So the original version of weighted A star in this HPA plus version said, yes, we should do re-expansions. But practically speaking, actually, I think that many people didn't do re-expansions. And if we look at what happens, at least this is on a grid world, we see that if I run weighted A star and I don't do re-expansions, I'm going to solve this problem relatively quickly. But when I do re-expansions, I'm actually getting really bad behavior on the right-hand side. So re-expansions can really be a problem for weighted A star. And the question is, well, how bad can they be? And the answer to this is to look at a general example here where we can grow this in general. And if we do this, what we create is the same sort of problem that we had before when we looked at A star. This is just a little bit modified to show weighted A star. And what we're going to see is the search is going to go across the top, and then it's going to do each of these paths going down, and then it's going to go back across and down and back across and down and back across, and then eventually get to the goal. So in this particular problem, we're going to get n squared re-expansions. Jingwei Chen, my former PhD student, was looked at the case of where it could be exponential in his thesis, but it's not in a paper that's been published standalone right now. So again, and this depends on the range of edge costs that you have. But the interesting thing is that I think many people historically have not done re-expansions in weighted A star because they haven't done re-expansions in A star. And Max Likachev showed in 2003 that re-expansions are optional, so we don't have to do them. So this theory was shown, and it points out to maybe a problem in the literature, which is we haven't been very careful, myself included, when we run experiments and things like this, of saying, if I'm using weighted A star, am I doing re-expansions or not? Because I might be secretly paying this overhead, and I need to be very careful about that. And so the question we wanted to ask is, well, if weighted A star doesn't have to do any re-expansions, are there other algorithms that also have the property of not having to do re-expansions? And I'm just going to go through this really quickly. Full understanding of this is too in-depth for the time that I have here. But let's take a look. So if we're going to write our priority function as f of n is equal to phi of h of n, g of n. So it's going to be a function of just h and g, not of anything else. There's some algorithms that might look at like the minimum f value in open or something like this. So we're not going to have access to any of that information. And the question is, what properties on this function phi would allow us to avoid doing re-expansions? We're also going to say we need a bounding function. A bounding function is a mapping between real numbers that's going to tell me how suboptimal I'm allowed to be. So for any x greater than 0, the bounding function of x has to be greater than x, because it says, I can't find a solution that's less than, optimal. There are no shorter paths than optimal. So b of w would just be w times n. That's the most common thing. But you could have something like b of gamma, which is n plus gamma. So that's an additive bound. Okay, and so these are described in detail in this paper. I'm going to show them to you here, but I'm not going to spend the time in this talk to go through all of these in detail. But we have this notion of these properties that we can write down, and any phi function that meets these properties is going to be able to avoid re-expansions. And if we look at what's going on here, and this question of re-expansions here. So let's describe what's going on in a search. So an A star search, on the left-hand side here, if we take all the states that are in the open list and we plot them over here on G and H, then each of them is a point over here. And what A star is equivalent to is taking a diagonal line, I'll draw it this way, but taking a diagonal line and sweeping it through the state space so that and we expand according to this diagonal line. So the states that are on the line get expanded before states that are above the line. And we're always going to expand the lowest states. So weighted A star, it ends up, is equivalent to not doing a 45-degree angle, but doing a steeper slope. We're going to write it in terms of phi functions to write it as g over w plus h. It's functionally equivalent. It just has to do with some of the constants in the proof that come out a little bit easier if you write it this way. And what the theory tells us is then there are other approaches that we could use that allow us to do very other interesting things. So one thing that works really well and is actually very, very robust across many different problems is phi is equal to 1 over 2w times g plus 2w minus 1h plus the square root of g minus h squared plus 4wgh. I don't know why anyone didn't invent this before we had the theory. Okay, I'm joking there. This is equivalent to a function of a parabola, which goes through this point down here with a slope of 1 and comes here with a slope of 2w minus 1. It ends up that you can't use a slope of higher than 2w minus 1 anywhere in this curve, but this curve, we can watch it run here, will allow us to run. It'll find the same bounded solutions that we found before. But because this curve is a little bit lower and some other properties, it ends up that it's actually much more efficient than weighted A star is on many, many, many problems. And what's going on here is that the slope of the curve is actually telling me my suboptimality. So what this says is at the beginning of the problem, I'm going to be optimal. And at the end of the problem, I'm going to be actually 2w minus 1 optimal. And if that's the case, 2w minus 1, that means I get to be much more suboptimal at the end than at the beginning. And if you think about it, at the beginning of the search, there aren't very many states there. So it makes sense at the beginning of the search to not be, not try and be optimal there. And then later on in the search, when there's more and more states to expand, we can increase our suboptimality. And basically, we get to distribute our suboptimality by redistributing it to be later in the search. Then we can be more effective in practice. Now we can go to the extreme, making this a piecewise function, where we're going to be exactly A star as long as G is less than H, And then with a normalizing constant out front, we're going to take the weight from W to 2W minus 1 when G is greater than H. And this works really well on really hard problems with a weak heuristic, but on really easy problems, it actually doesn't work very well because we're running A star when we don't need to run A star. So this is something else we can do. We could also reverse this. We could be highly suboptimal at the beginning and be optimal at the end. This generally doesn't work very well because it's a lot of work to solve that last part of the problem optimally. So that doesn't work well. Although it can work well with very, very large weights on some problems. Okay, so if we think about weighted A star, and again, we've been looking at everything with the lens of re-expansions. There's been a lot of work on weighted A star that hasn't really thought about what are the impact of revisits. Are we doing revisits or not? And need to just clearly say that in our research. But given that we want to build a priority function that has the potential to avoid re-expansions, of course, you could still do re-expansions here if you wanted to. If, for instance, re-expansions didn't have a huge cost, that's fine. Do the re-expansions. You still get to distribute your suboptimality, right? So what we've learned from this of thinking about avoiding re-expansions doesn't just apply to that one thing. It's actually taught us something deeper about the way that we can shift our suboptimality across the problem. And so it's given this insight. Thinking about re-expansions, it's given us insight into how we can control where the suboptimality arises. And that allows us to finish this picture for today. Gives us weighted A star that doesn't do reopenings. It doesn't need to do reopenings, but if it does, it'd be 2 to the n. My picture here is covering it could be n squared, again, depending on your exact assumptions. But if we do breadth first search with no re-expansions with our phi functions that meet those particular conditions, then we can entirely avoid doing re-expansions. So to summarize this talk, the notion of doing re-expansions seems to be very tightly coupled with the notion of consistency. Is a very fundamental concept that cuts across many, many, many search algorithms. And recently, by analyzing these cases in bidirectional search, suboptimal search, optimal search, and all of these cases, we've been able to actually have significant theoretical improvements in the worst case of these algorithms by thinking about these questions and by designing algorithms that compensate for that or are able to adjust for it. So there's a couple open questions here. One question that we see is we can take A star and we can get that has this worst case of n squared, or algorithm B that has n squared, and we can take it to n log C star. And the question is there something like a Bellman of Ford equivalent that we can get n log C star? That is, can we port that problem across? One of the questions here is if I could take a Dijkstra's algorithm with an inconsistent heuristic and I could extract it out into a set of costs of non-negative edge costs and heuristics, then we could actually go and apply this. But all the ways that I know how to do this are actually going to be at least n squared time, so we actually don't see any gain there. So there's a question to either prove that this is just going to be n squared. We can't take advantage of the decoupling we have in A star between the inconsistency and the edge cost all being positive or not negative, or to figure out how to do this. So that's an interesting open question that's there. And there's another question. We've seen that A star we can take the worst case from n squared. So could we do this for weighted A star? And this is more complicated than it seems because we don't have this notion of necessary expansions. And so in practice, it's not clear if it's possible or if it's useful or something else there. But it is an open question. Now, if you're interested in learning more about this, I took this picture that I generated earlier. I turned it into a QR code. This just takes you to movingai.com, but you can see I've got a lot of demos here. So Dijkstra's, weighted A star, suboptimal search, looking at re-expansions, and there's an entire YouTube channel that I have, which is a graduate course which goes into many of these topics. But hopefully this overview here of looking at re-expansions across a broad number of algorithms interesting. It's given maybe you some more insights and understanding of the algorithms, and hopefully maybe will influence the way that you do things in the future, help us be better researchers, for those of you who are researchers, or to learn about some new applications, some new algorithms that might be able to be applied in practice. And I'd be glad to, if you have any questions about any of this, I'd be glad to answer questions that show up in the comments. I'm always paying attention to those and trying to respond. But thank you for your attention here, and we're going to finish up here. So thank you.